All right, we're going to start section 3.4, which is on velocity and other rates of change. So the first thing that we're going to look at is instantaneous rates of change. We've already looked at the difference quotient several times, f of x plus h minus f of x over h. And we can think of that as the average rate of change of the function over the interval from x to x plus some small value h. The instantaneous rate of change, which we often just refer to as the rate of change of our function with respect to x, at any value, x equals a, is just the derivative of our function at that value a. So we're going to look at some real-world examples, some story problems. I know those are your guys' favorites. So with our first example, a company makes computer chips from square wafers of silicon. It wants to keep the side length of a wafer very close to 15 millimeters, and it wants to know how the area, A of x, of a wafer changes when the side length, x, changes. So we're going to do two things here. We're going to find the rate of change of the area of a wafer with side length 15 millimeters, and then we want to know what would be the appropriate units for the derivative of A with respect to x. So let's think about this silicon wafer that the company is making. It's square-shaped. You know about the area of a square. You know that it's just the side length squared. So we can say that the area with respect to x is going to be x squared. So then, using our derivative rules that we learned in the last section, we know that the derivative, a prime of x, is just going to be 2x. So if we want the side lengths to be very close to 15 millimeters, then the derivative of our area, looking at that 15 millimeters, would just be 2 times 15, or 30. So the rate of change of the area of a wafer with side length 15 millimeters is 30. Well, what kind of units should we put on this? It's our follow-up question here. Let's think about the units involved. If we're looking at the area of our square, we have our side length squared, the area of our wafer. If our side lengths are millimeters and we're squaring them, then the units on that would be millimeters squared. We also have x involved here, our side length. And our side length, we're just measuring in millimeters. So here, the appropriate units for our derivative dA dx, remember this is just another way of saying a prime of x. Our appropriate units would be, well, A of x was dealing with millimeters squared, so we have millimeters squared of area per x was dealing with the side length, which we measured in millimeters. So we have millimeters squared of area per millimeters of side length. And you might look at that and go, can't we just simplify that to millimeters? Well, no, we can't, because we're looking at two different sorts of units here. We're looking at the millimeters squared of area and the millimeters of side length. So we have to say something per something, just like when we're looking at other rates of change and we look at miles per hour, that sort of thing. So it's always going to be whatever we're looking at in the numerator, how we would measure that, per whatever we're looking at in the denominator, how we would measure that.